Okay, welcome everybody. It's a pleasure for me to introduce to you today our guest lecturer from University of Texas at Arlington, Professor Zdzislaw Musielak, who is going to give a talk today on the unsolved mysteries of our universe. Professor Musielak has a PhD from the University of Gdańsk in Poland. He has worked, for example, at the University of Gdańsk, at the University of Heidelberg in Germany, at the Massachusetts Institute of Technology. He has worked at the NASA Marshall Space Flight Center, University of Alabama, and now finally at the University of Texas, where he is professor at the moment, and also director of the UTA astronomy program. He has received numerous awards, including the Alexander von Humboldt Research Award and the Humboldt Follow-up Research Awards. His research focus is on extrasolar planets and on the origin of dark matter and dark energy. So please welcome Mr. Professor Musielak.
Thank you very much. I hope, can you all hear me? Oh, yes. Great. Thank you very much for this introduction. I am really happy to be in Norway. This is my first time visiting your beautiful country. Yesterday I spent the whole day moving around Oslo and seeing very nice capital that you have. And today my friend brought me to your pretty city here. And I'm really delighted to be here and have opportunity to talk to you about things which are of very strong current interest. And what I'm going to do, I'm going to give you a little bit overview, but the purpose of this lecture is to point certain very well-established facts, but at the same time, things that we completely do not understand. And we do not know why things are the way they are. Why am I going to emphasize this? Because I see a lot of young people here, and we do need young brains who can solve. We need new Einsteins who would solve completely unsolved problems of the universe. These are so fundamental, and I hope you get this out of my lecture. I will be moving with certain pace, but if this is okay with Mr. Chairman, it's okay if somebody stops me and asks questions. I have no problems with that, okay? So let me just start by showing you a couple of pictures where I live. I live in the Metroplex, which is Dallas-Fort Worth area. This is Texas. And population of that Metroplex is around 7 million people. Texas has population of 28.5 million, and as long as the size is concerned, is the largest state on the continent of the US after Alaska, and it's twice of the size of Norway. That's Dallas. Dallas is the main city. This is downtown Dallas. It's unfortunately known for the fact that President Kennedy was killed there, but beside that, it has a lot to offer. It's a city, very modern city as you see it, with a lot of things going on there. Here's Forward. Forward is the old-fashioned Old West type of city. As you may see here, that's the downtown of Forward. If you move a little bit west from it, you would find pictures like this, which is pretty unusual because this is modern United States. It's 21st century, and if you go to the place in Forward called Stockyard, you actually can meet true cowboys, like you see here, okay? And twice a year, they have those cows that they bring them there. So, you know, it's a lot of activities and a lot of interesting things. Actually, at the time, this bunch of cowboys that you see on that picture, those are Hollywood actors who were there to record a movie. Interesting things. Now, I work at the University of Texas. In Arlington, we have several campuses. It's a very large university, has 57,000 students. And you may see, look at the pictures. The picture up there is showing a campus. Our campus is always very busy with students. This is building where my office is somewhere here at the end. This is our planetarium. And it's very nice campus overall that you may not see all the details here, but nevertheless, it's very, very nice, very lively campus with a lot of activities and a lot of students being there present. What I like to concentrate on is on science and scientific achievements. And science is absolutely amazing. I want to especially emphasize this point to young people in the audience who may not yet be aware of the fact and who may basically say, well, why should I study physics or mathematics? Science is everything in the following sense. Physics underlines everything what we currently know. Look, I started listing here, but obviously I didn't. My list is not complete. I said computers, smartphones, TV, and so on and so on. Everything is because of physics. Everything is because what we know is because of the physical laws that we understand and physical laws which were used to construct those devices. Now, as long as the achievements of science are concerned, is also this great, absolutely great improvement in understanding of the universe and in kind of getting overall picture in the world where we live in. This is absolutely amazing what has been done within the last century or so. It's absolutely amazing. And I will try to bring this a little bit to your attention to show you that what we have achieved and where we stand currently is pretty amazing. But what is even more amazing, that we learned so many things that there's a large areas, not one, large areas that we actually do not understand what is going on. I want you to look at these pictures, and those pictures show some very, I call it bright spots. Let me just move here so I can see it also. You see our home, our Earth, some extrasolar planets, some very peculiar stars. This is all things, these things all exist in sky somewhere. Our sun, you haven't seen picture like this of the sun. What you see here is the solar corona, how active and how interesting, intrigued it is. Here you see stellar jewel box, which is a group of very bright, very interesting stars located in Magellanic Cloud, and very beautiful Whirlpool galaxy. But in addition to that, our universe has also something which, oops, I'm going wrong direction, something which is called dark sides. And my talk will concentrate on those dark sides. Why it will concentrate on dark sides? Because that's what we know, that these dark sides are there, but we really do not know what they are. So I want you to pay special attention to three things about my talk. First will be the concept of dark energy and how is it related to what we know currently about the universe. This will be explained later. The concept of dark matter, and we will start with a black hole, which is the strange, very weird object. Is one of the weirdest objects ever discovered by astronomers. what is the most challenging thing in our current understanding of the universe? I want you to, maybe I show this picture also at the end of my talk, because I want you really to, if you take anything with you home, I want you to take this picture home. This is like a pie, right? You see it like a pie. I don't know whether you've seen this or not. This pie has the most challenging problems stated in the simplest one chart. What do you see here? You see here that there's a dark energy which has 73% of all the energy in the universe, and cold dark matter, or dark matter, which is 23%. We do not know what is dark energy. I am getting ahead of myself with my talk, but I want you to know that. We do not know what is dark matter. I will try to tell you what we currently know and how we know that it exists. And we still do not know what they are. All what we know about the current universe is this 4% of atoms. So if I would put a test, and in my test I would ask questions, what would be your answer if I would ask how much currently physics knows, the laws of physics that we currently know, where they apply? They apply only to 4% of matter in the universe. 96% is completely unknown. We live in the golden age of science, golden age of physics, study physics, golden age of astronomy. Why? Because we just know only 4% of the universe. We do not know 96% what the universe is built of. That's kind of surprising, right? Because you would not expect that. You should ask me, stop me and ask me, so where is this dark energy? Where is this dark matter? Well, can I see dark matter here? Can I see dark energy here? That would be a very good question to ask. If you don't ask, then I ask you, and let's see whether you could answer my question at the end of the talk. Okay, but first we need to go through this to understand that. Physics is based on two fundamental theories. One was produced by Einstein, and the other one, it's called general theory of relativity. The other one, it's called quantum field theory, and you will have some glimpse of it. I will just say a few words about both. We will start with Einstein. You see, 2 years ago, we celebrated 100 years of Einstein theory. General theory of relativity is the theory which tells us a lot about universe, about evolution of the universe. All what we know comes from Einstein's general theory of relativity. All what we know about the universe. What is general theory of relativity? Is anybody who knows? What is general theory of relativity? It is something very simple. Einstein had extremely simple idea. What is gravity according to Newton? It's just action between two masses, right? But what kind of action? Well, it's a force, right? Acting between two masses. Einstein had different idea. What did he say? He said that the space is not by itself, it's space-time. So you have a curved space-time. And when you have a curvature of space-time, then the curvature is corresponding to the gravitational force. That's it. This is all. So all what it is the space-time, not space, no time, but space-time together. And then when it's curved, you have gravity, which is explained by the curvature. You see here the light bands, the curvature in the space-time causes this ball here to be pulled down. This is all what it is. Now, everybody is kind of familiar with this. Have you seen this before? Students, have you seen this before? I think you kind of heard probably that, right? This is all what it is. Now, the question, very good question to ask, is this. What happens if the curvature gets stronger and stronger and kind of closes completely up, right? What happens then? That is a very interesting question. So let's get to it. What happens is if you have black holes, they are very exotic, but they are also very scary. How scary they are? Oh, they are pretty scary. And I will try to explain to you why they are so scary. Because it looks to us like what we are currently understand, that black holes eat everything what is in the neighborhood. Doesn't allow for anything to be close to it. It's like a monster. It's like a monster which destroys stars, which just cleans up the surrounding. I want to specifically concentrate on 2 points. What do we know and what we would like to know? The person who Einstein didn't solve, Einstein did not predict the existence of black holes. It was Schwarzschild. Schwarzschild was, can you believe it? The guy was at the East Front in the First World War. And what he did there, he was a soldier, German soldier, fighting against Russians. When bullets were flying around, he was sitting in the corner and solving Einstein equations. And it's pretty unusual surrounding to have somebody who sits when bullets, Russians are shooting, flying, and the guy doesn't pay attention to the bullets, but that's how devoted he was. And he sits and writes on a piece of paper and he solves these problems. From the front, he sends Einstein a letter with the solutions. Einstein looks and he said, no, my equations cannot predict something like that. Because Schwarzschild showed that all light and everything goes inside, that black hole is a monster which only takes things in, but never gives anything out. Einstein said, this cannot exist. Cannot exist in nature. Guess who was right, who was wrong? Einstein was wrong. Schwarzschild was right, because astronomers discovered these things. What is a black hole? I want you to remember only one picture. As long as the black hole is concerned, the structure. What is the black hole? The black hole has only two really important features. Where is my pointer? The one important feature is singularity. Do you see it, singularity? Singularity is the point at the center. And at this point, singularity is a very strange thing, because Einstein theory collapses there. We cannot say much about singularity because there's no physics, there's no physical theory which would deal with singularity. The other point is even horizon. If you cross even horizon, it's a point of no return, which means you can be close to the black hole, but once you close the even horizon, the black hole takes over and you can never get out. Okay, ladies. I know that ladies like mirrors and comb their hair and thing. I suggest that if you were able to travel very close to a black hole on an orbit, which is circular orbit, not far away from the even horizon, but it has to be circular, then photons of light would be connected with you, would be traveling with you, and actually for the first time you will be seeing your face and also the back of your head. You will be able to comb, ladies, your hair without having mirror or anything, because you will see back of your body and front of your body. Pretty peculiar, right? Why is that? Because light does the same thing, travels with you. It's trapped. It travels with you on this orbit. Well, there's more to it. This is not the end of the story. The question is this: what happens when you have an object which is thrown inside black hole? Or when you have a person who is going down towards the event horizon. then what happens? Well, the gravitational force, as you see, here's the black hole somewhere. And what is happening, that the gravitational force on the feet of that person is acting much more stronger. This is very strong gravitational force than on the head. So what is happening? That the guy who is coming and approaching the event horizon gets thinner and thinner and thinner. His legs get longer and longer. His body, obviously, he cannot survive that, but in science, don't think that scientists are always serious people. You may think that our scientists are very serious people who sit and solve equations. Not really. Let me show you why. They introduce a name. Oh dear. Did I mess up something? No. Spaghettification. No, everything is okay. Spaghettification. Have you heard this name? This is making spaghetti. But this time we are making spaghetti, unfortunately, out of the person who is falling to black hole. Oh, what a name, right? Do you know that it's official name? Spaghettification. I want you to remember that, right? Pretty strange. Next time when you eat spaghetti, just concentrate on spaghetti. Don't think about spaghettification. But that's what it is. It is actually a way for the black hole to make a person mile long. That's what black hole can do. How astronomers think about black hole? This is the way they think about black hole. So what it is a very strange, peculiar region in space-time where everything goes inside. So we see event horizon, and everything what happens, what gets close to it, goes inside and goes to singularity. This is all what we know. What we would like to know, that what happens when the matter enters? Where does it go? Well, one option is that it reaches that singularity, and maybe that singularity is a connection to another world. Maybe we are connecting to another universe. How? What about something like this? You enter through one of them. It's like science fiction. But actually, don't think that this is science fiction, because now scientists actually are doing this work, and these are not speculations. This is actually something that scientists are studying, thinking that there could be another universe, and that other universe we could connect through that loop. That loop could really connect us to another. But obviously nobody wants to jump in. Once you jump in, you cannot come back. So what do we know? What do we know about black holes? We know that they exist in the universe. We know that traveling can be interesting near them. That event horizon is a point of no return. Means once you get to it, you have to go inside. This is all what it is. What we would like to know, we would like to know a lot. But the most important is that existence of singularity. We know that singularity exists, but we do not know why. We do not know how to remove it. And we do not know whether this means that we have connection somewhere else. That's where the physics stops. Physics is very powerful, but this is the limit of physics. Physics cannot tell you what is singularity. Physicists are very frustrated that they just cannot. So that's one of the open region or open area for young people to start studying this, and hopefully somebody will solve. Now, Einstein theory can also be used to describe how the universe evolves, how the universe changes. Here's what we approximately know about the universe. We know that it came into existence through some big bang, which is a very big explosion, and then it developed until to the modern universe by just forming through different stages. I'm not going to describe that because this is not really that critical for my talk. I would rather concentrate on the following issue. The Big Bang. There were two scientists. If you ask any astronomer or physicist, you probably heard about Hubble Space Telescope. Hubble is credited with the discovery of the expansion of the universe. But it happened that 2 years before Hubble published his results, Lemaitre, the Belgian priest, Catholic priest, actually published similar results. And now there's the discussion whether Hubble expansion of the universe should be called Hubble-Lemaitre expansion of the universe. But I want to show, especially students, a couple of pictures so you see what was the science like by Hubble when he predicted something so powerful that the universe is expanding. So here's what Hubble showed. Hubble studied how, this is Doppler effect. You probably know Doppler effect, how lines are shifted when the object is moving away from us. You see the arrows show how far the lines are shifted. From there you can determine velocity with which the object moves away from us. So all what you need are those velocities, and then what you need to plot how distance and the velocity depend on each other. Based on this line, look how powerful is science. This line that I am showing you is the greatest discovery of 20th century in physics and in astronomy. It shows that our universe is expanding, and it is just straight line. Just straight line, right? And these are the actual data taken from Hubble and from some others. You see how straight. So what does this mean? Oh, it means that every galaxy which is farther away from us moves away from us with certain speed. Farther it is, faster it moves. So look, this distance increases. The distance increases. And the distance, so when you go backward in time, the distance between those galaxies was smaller and smaller, and then eventually, well, they had to come up into existence. So that's how the expanding universe is explained. So, another point, very important point, it was Hubble who is credited, but now probably credit will go also to that priest. So anyway, this is what I already said. Now the Big Bang by itself has similar singularity, which means we do not know what is the Big Bang. We do not know what happened at the Big Bang. And that's what we really would like to know. There are many unanswered questions. Many unanswered questions. One is, what really happened? Why there was a Big Bang? Why our universe in the first place got created or came into existence at the Big Bang, at the t equal 0. Now, if you ask astronomers, they would say time was created also at that point. So the Big Bang, we got time and space and everything came into existence, right? That's what astronomers currently believe. All what we know, the whole universe came into existence at that particular point, the Big Bang. So what is the main goal of science? Is to understand that point. And what is the most frustrating point of science is that we cannot. That we just don't know what happened there. We just don't know. And any questions, asking questions about the beginning of the universe is pretty tricky. I tell you why. When people try to give hard time to St. Augustine and ask him whether time. Now, actually, the question which was posted was differently, was like this. So, St. Augustine, what God did before he created time and space? That was the question that scientists asked St. Augustine, who was a philosopher. And he was scratching his head, he was thinking, and he obviously didn't have any answer to that. So he said, God created hell for people who ask questions like that. I mean, that was pretty much his answer, because he didn't know how to answer that questions. And he was a philosopher. We scientists, we don't know how to answer that question. So, the problem of the beginning of the universe is a fundamental problem. Now, the great discovery was made in 1995 or so, or 6. The discovery was made by studying very distant objects. They discover that the universe is actually accelerating right now. That when we speak, the universe is speeding up, not slowing down. The universe, the initial expansion should slow down, but it's not. It's actually, the universe, it's actually expanding faster and faster. And everybody was puzzled. Why? That's what it shows. Can you see it here? That's a very nice cartoon or picture. You need to go here to also see better. So here what you see, first what happened, the universe slows down after the Big Bang. And now suddenly, starting from here, it starts speeding up. The big question was why? What is causing that? This is another plot which shows essentially the accelerating universe and those points which are along the straight line, but as you see, those points are a little bit above that straight line, which is Hubble line, the one that I showed you before. So you see these points which are located here is the indication of accelerating universe. This is the actual plot for which 3 people got Nobel Prize. Can you believe it? One plot like this, points which were just above the Hubble points, and you got Nobel Prize. But this essentially means one thing. These 3 people got Nobel Prize in 2011, and this is an indication of the dark energy. So astronomers concluded that the universe is accelerating because of the dark energy. So what is dark energy? I wish we knew. Where does dark energy come from? I wish we knew. What are other effects of dark energy on our universe? Well, we are studying that. Do we have ideas about what dark energy is? Yeah. Oh yeah. We know very well. We have a bunch of ideas. These are all ideas. It would take me 40 minutes for each one of these ideas to present to you in details and to tell you what it is. But why spend your time and my time, as at the end of the talk, I would have to say, well, but it may not work. Okay? You see my point? So, scientists are full of ideas. We can read them. I can tell you if you are interested what they mean. But the bottom line, the very bottom line is nobody knows. Nobody knows what is dark energy. Nobody knows what is dark energy. When we thought that dark energy was one problem that we cannot solve, well, we realized that there was another problem. Dark matter. So remember these dark sides of the universe when I show you the pictures? Dark matter, dark energy, black hole, also kind of black. Here are 2 people who are credited for discovering of dark matter. Do you see this person above? Zwicky? He was very kind of mad scientist. He argued with everybody. kind of, it's enough to look at him, right? He argued with everybody, but he had a very good idea. He had an idea, he studied galaxies. And if those galaxies were too close to each other, they move with certain velocities. Maybe I show you the next picture. We come back to this lady in a moment. So what he said this. You see, this is at the center, there are galaxies. And if these galaxies are not surrounded by dark matter, they would all escape. They would not stay together. So he had this idea in 1932 or 33, very early. He had this idea, and he argued with everybody. He said, I am telling you that there's dark matter, and everybody laughed in his face. But later on, this lady, let me show you her picture. She just passed away last Christmas. Vera Rubin, 1970, she showed another evidence for the existence of dark matter. The evidence is that if you have stars like this, you have a galaxy which is full of stars. What you see there, you see there a star. I can pick a star, one here star or something. Or what you see that the galaxy rotates like this. And if you move away from the center, the stars are supposed to move slower, right? Because of the gravitational force, which is decreasing with distance. But it happens that the stars don't move slower. Those straight lines show that the stars actually move with the same pretty much speed. Do you see those lines? The lines are flat, which means stars even at the edge move fast. So what is the explanation for that? Oh, astronomers came up only with one idea, that there must be dark matter. Oh, this is in Polish. I'm sorry. It's a dark matter. And this dark matter, this is the galaxy, and this is the dark halo. A halo of dark matter which is required to explain those curves that I just show you, those flat curves. So, what is dark matter? Well, that's another good question. I wish we knew. We do not know what is dark matter. People speculate, thinking that maybe these are some particles. Look at the names of those particles. Macho particle, and WIMP. WIMP actually doesn't mean really WIMP. You know what I mean? It means weakly interacting massive particle. So it has a certain meaning. It's WIMP. So we are looking now for WIMPs, or we are looking for SUSY, supersymmetric particles, thinking that those particles, if we find them, they could be dark matter. Well, this is one of the experiments. I'm not going to describe it, but it's one of the experiments called Xenon experiment, very well-established experiment in the US, and obviously the results are completely negative. I could spend 30 minutes describing the experiment, but so far they got nothing. Nothing means they didn't find that particle. So we have to look, maybe there are some other particles. You know, this is a standard model, which I will not probably get into this, but CERN, have you heard about CERN? Who heard about CERN? Everybody heard about CERN. What was the greatest discovery of CERN lately? The greatest discovery of CERN was? I saw so many hands, so that's very nice. It's a European main center to smash particles and produce new particles, right? And what was the new particle that they produced? Higgs. Very good. Very good answer. Excellent answer. Let me just go back and quickly. Do you see that Higgs there? I put it in the middle. This is standard model. All particles that we know. I'm not going to describe this, but you know, everybody probably heard about quarks, leptons, forces carriers, but the important thing, what you see there, is that Higgs, which I put in the middle. And the quantum field theory is the field which is the theory which unifies the forces and gives the structure of all the matter. But anyway, the CERN is looking for new particles, thinking that maybe those particles are particles which could be dark matter. Could be dark matter. That's a Large Hadron Collider, LHC. Do you know how big it is? Is it bigger than this building? If you want to have an idea, let me just show. Do you see the human there? Who sees the human? Everybody sees the human, right? Look, that's the human. So this is what? Several stories high, right? So it's probably comparable to this building. So what happens? Particles collide there, then they are smashed there, they collide, and then all these things that you see there, these are different detectors which detect what came out of these collisions. Very interesting work. Atlas detector was constructed partially at my university by a group of high-energy physicists. Okay, so what is the main problem? Well, the main problem is this. CERN, all experiments look for dark matter particle, found nothing. CERN look for dark matter particle, found nothing. Theoreticians like me, I am pretty much theoretician, we would like to do the following. I told you at the beginning, right, that we have two theories. One is general theory of relativity. The other one is quantum field theory. And the bottom line is how in the world we can put these two completely different theories together. This is the question. General theory of relativity operates on the scale, grand scale of the whole universe. Quantum field theory operates on small scale, very small scale, atoms and below. So the question is how to combine macro and micro. How to put this together. Einstein tried for 35 years of his life. He spent 35 years of his life trying to put these things together. He failed. Everybody who is in this business try it. Guess what? Everybody so far failed. Nobody knows how to do it. We think that once you do it, you will have the answer to dark energy, the answer to singularity, the answer to the existence of black holes. This theory will tell you and answer all the questions that I posted as a questions. Okay? This theory will answer. However, these are speculations. We do not know how to unify this theory. I'd like to show you something, since you are all Norwegians, and you are, or most of you, not all, but most of you, and I am assuming that you know two of my favorite mathematicians. Do you all know that? Students, do you all know these two mathematicians? Abel, you can find his HUBBLE, you can find his statue on the University of Oslo, and it's even in the park near the Royal Palace. It's also there, but it's kind of a slightly different picture. They actually developed, why I'm mentioning their names, first of all, they are my favorite, because I'm also working in similar area what they have been doing, what they had done. But they also developed certain regions of mathematics which are used for current unification theories, which means what they developed, we try to actually accommodate and use their theories to maybe put this unification which is still missing. I want you to really always try to give them credit, especially HUBBLE, who died being 20, do I remember correctly, 25 or 26 or something, right? Very, very early. It's amazing what he would probably do. Those were mathematical geniuses. It's pretty much if you start thinking what kind of achievements he could make if he would live up to 80s, is beyond words. But this is all speculations. I want you to keep this too in your mind. Now, I still have a couple of minutes. I will try to wrap this up as we planned. But I'd like you to listen to one more topic. So you see, now hopefully, let me just briefly summarize what I said so far before we get to this. What I said so far is the following, that we have three major issues, or four major issues in science. The existence of dark energy, dark matter, singularities, the beginning of the universe and its existence. And we just cannot solve these problems. We do not know how. Now, I'm thinking for a moment when it happened. Excuse me, but I think it happened around 1994 or 1995, when first planet was discovered at a distant star. These are like our planets, except that they are far away at distant stars. Why it was a big deal? Because astronomers talk about planets around stars for years, but they never were able to discover them. We now know, look, 3,600 planets. They are called exoplanets. Very quickly, how do we know that they exist? Two observational techniques. I just want you to remember those two techniques. How maybe let me just I better move here because I don't see when I stay too close. So look what happens. Look what happens when a planet moves around a star. What happens to a star? The star wobbles, moves slightly, right? And we have right now very good technology, so we can actually see how the star moves, how the star wobbles. That's what tells us. It's not that we see the planet. You see my point? We see the motions of that star. And as a result, we can conclude what kind of planet is there and so on and so on. Using Doppler effect. The other technique is so-called transit method. Look what happens. If the planet is in transit, we observe a star, and there's some little dip here. This is brightness of the star. Changes. You see it? Changes. And then it comes back when the planet disappears. We can measure this, and from there determine that there's a planet. Pretty neat, right? I mean, I'm telling you that technology is unbelievable, that you can do this kind of measurements, which 30 years ago, nobody even dreamed about this. And right now, you can do it like this. It's pretty actually amazing. So, we discover many planets, 3,600 or something. Some are very hot, very hot. Some are very cold, very cold. What are we after? Oh, we are after finding a planet which would look like our Earth. NASA put a lot of money because of public relationships in the US. They spent a lot of money trying to find a planet which potentially could look like our Earth. Why? Well, because they think that this will be the first greatest discovery ever in science, discovery of life outside of Earth, right? So that's pretty much how we all feel. And again, this, I wanted to show you this, my very favorite. When I was young, I read a lot about Amundsen, and he was a great explorer. As we know, he was first who reached South Pole, and we in a sense follow his steps in searching this time for life outside our Earth. But you know, we are doing this similar way he made his preparations and getting first to the South Pole. It is part of, you know, our activities as scientists, try to find the Earth-like planet. Just to wrap this up, let me just say very exciting discovery, because you may say how far these planets are. Well, they are unfortunately pretty far away from us, because stars are far away from our sun. However, look, not a long time ago, well, first I show you this and then you will see it. A discovery was made. This is the Alpha Centauri system. It's a triple system. Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, they are the closest stars to our sun, the closest one. What is the most amazing thing is that, look, comparison. Sun is almost like Alpha Centauri. Alpha Centauri B is a little bit dimmer. And then you see Proxima Centauri. What was the most amazing thing? That the planet was found around Proxima Centauri. And that planet is very similar to our Earth. So guess what? Some people in the US already are planning to send a robot who would go and explore that planet, because they think that not in our lifetime, not even probably in your lifetime, but it may take a couple of generations that thing finally reaches there. But remember, it's like 4 light years, which means if that spacecraft, let's say we send spacecraft, it arrives there, it sends signal, it will take 4 years to come back, right? To say, I arrive. Well, we will see it arrive, but it will take 4 years. Then we will say, we do this. It will take again 4 years, to communicate with that thing. But why it's so exciting? Because it's very close. It is so close to us that this could be the case, that indeed we have, now this star, that we have a neighbors, but studies still have to be done. This is not true. This is just to summarize these things and show you parameters of star, which is on the right, and the planet, so the planet is comparable to the Earth. The star is much, much smaller and much, much cooler. So just one particular thing about it. This planet, it's so close to that star that if somebody lived there, the year would be 11 days long, right? Only 11 days. It takes 11 days to complete one full circle orbit. Now, and my time is practically up, but I like to very quickly, without getting into details, to tell you only a couple of things. You see, we have an exoplanet research group. You see members of that group at my university, and you see all students who are involved in it. And we do some kind of very interesting orbital studies. My student, Marialis Rosario Franco, she is from Puerto Rico. She's doing searches for exomoons this time, not exoplanets, but exomoons, using radio data from GMRT, which is a very major telescope in India. So, and we are doing this work because there's a lot of interest these days in finding the first exomoon as well. So we are kind of in a little race. You know what I mean? Like racing. Who is going? There are 3,600 planets, and discovering one more planet is like no big deal. But the question is, who is going to be first to discover the first exomoon? So my student, this lady that I mentioned, she is just like this, eager to be first to discover. I said, if you discover that, you will be famous. So let her be famous, right? But she's working very hard on that. We are in the race. We are competing with Colombia. We are competing with a couple of other places in the US, as well as with Puerto Rico, Arecibo Observatory, and some others. Everybody is trying to find the first exomoon. Why? Because maybe in some distant planets, life is on exomoons, not on moons. Okay, and the other group, and this is my last chart, the other group is I'm also in charge of physics theory group, where we go really wild with our ideas. And one of my students, Mohammed Latifi, who is from Iran, he's studying currently some extra time dimensions. He's really a mathematician. And my other student, Gordon Cannon, is studying physical processes very close to the event horizon. So we are studying essentially black holes and things which happen near singularity, some cold dark matter. So these are the studies that we do, but in the studies, we are mainly looking for some new ideas which potentially can solve one of the unsolved problems in current physics. So I think this pretty much concludes my presentation, and I would like to thank you so much for your attention. And if you have any questions, I'll be more than happy to answer, but I let the chairman to decide what do we do from now, right?
Okay. Okay, so we are short in time, but we may have time for a quick question or two. If we...
Or I can wait a little bit and talk afterwards if you have something else scheduled. If there's interest in that, right?
Okay. So any questions at the moment?
Yes, Mark.
I have two questions. One is this precise amount of dark matter, dark energy, 73%, 20-something. If we don't know what these substances are, how can we establish this?
Oh, this is established by very good question. Excellent question. Oh, the second.
You asked this question. This is just idea which came. And the second question is, when we unified this general theory of relativity and quantum field theory, how do we know that the results would be called dark matter, dark energy, singularity?
Well, Right. Well, singularity occurs first. Maybe I should go with the first question, right? We have a very precise measurements from several instruments which determine this is how fast the universe expands, so we can say how much dark energy is there. Then we have very precise way to determine how much dark matter you need in order to explain the observation. So this is very precisely established by astronomers. However, we do know what it is, which is a different story, right? So we do not know what it is, we know that it's there, which is very frustrating from the point of view of astronomical point of view, but on the other hand, it's very interesting to live during the time when there's so many open areas to do the, right? Yeah. So now, well, maybe I answer your question, the next one, right? Address a little bit later. If there are no more questions, I let the chairman to, yeah, go ahead.
Okay. One more.
One more question. If I understood you correctly, it's the 4% we know
Yes.
that obey the known.
This is all the matter that we are built for.
My question. It's the 4% that obey our known physical laws, but dark matter, dark energy, we're not sure that they actually obey these laws. So how can you then calculate the percentages when you don't know if they follow the same laws?
Now, we do know how much is there from what we do not know, for example, what kind of matter is dark matter, right? Yeah. Right? We just do not know. This is not regular atoms that our body is built of, that our Earth is built of. The reason is that if it were, then it would interact using all the forces that we know, like weak force, electromagnetic force, but it doesn't. It's dark, black, and it does not interact through any forces except gravity. This is all what is established, which means the lack of interaction through other forces implies that this is a different animal in that zoo. And we need to figure out what it is. So very likely it's a different particle outside what is known as a standard model, which applies to all matter that we are familiar with. So that's where we stand right now.
Yeah, but it would seem to me that you would need the standard physical laws, you would need the interaction laws to calculate those percentages. But you imply that these laws don't necessarily apply in this case. And
This
then
could
you
be,
have
it could be the same physical law which applies to regular matter. This is a very good point, to the same regular matter. However, if this is the same law, the particle by itself could be different. This is, I want you to understand, for example, dark matter. Let's concentrate on dark matter, okay? The particle is something which we need to find because it could be a different particle, like we found Higgs, which is a completely different particle than all other particles. You see, the plan is to find that new particle and see how does it fit. And then we will know how it extends from a regular to dark matter, but physics laws not necessarily change. Gravitational law is the same. Dark matter we could measure because we assume that it acts by gravity, and it does, because otherwise stars would not move the way I showed they move. So everything fits together except what it is.
Okay, thank you everybody for your questions.
So I will switch this off now.
Yeah,
And I give you this, right?
I will give you just a little small appreciation from University College for your excellent talk.
Oh,
So-
well, thank you so much.
so
I do
thank you
appreciate
for,
this.
coming
Thank
to
you.
our place.
Thank you. And I give you in return
Okay,
this thing,
yes.
if this works, right?
So.